Greetings, AP Chemistry students. Today, we're going to be talking about periodic trends. And you should have learned about periodic trends before, but what's critically important in AP Chemistry is that you can explain why the periodic trends occur. Because you're going to have your first test on Friday, and as part of that first test are going to be some free response questions where you need to be able to give a clear and concise rationale as to why a trend happens. And I'm going to tell you now that position on the periodic table is not why a trend happens. The periodic table is arranged based on the fact that these properties exist, but they're not a fundamental reason why, for instance, one atom has a larger radius than another, right? So the first trend we've got is atomic radius, which is essentially, the size of the atom, the distance from the nucleus to the edge of the electron cloud. And the trend for atomic radius is that radius decreases as you go from left to right on the periodic table because you're increasing the nuclear charge. You're adding more protons. It pulls everything closer together. But then it increases as you go from top to bottom because you're adding new energy levels or shells that are further from the nucleus. So that's the trend for atomic radius. And there's a chart on the next slide. But if we look at this periodic table right here, you'll notice that as you go from left to right, from sodium to magnesium to aluminum, silicon, phosphorus, sulfur, chlorine, and argon, as you go from left to right, the radius gets smaller because even though you're adding more protons, you're also adding more electrons to the electron cloud. You're also adding more protons to the nucleus, and so based off of Coulomb's law, that pulls everything in closer together. But as you go from argon to potassium, sure, you add another proton, but potassium's 19th electron goes in the 4s sublevel, which is much further away from the nucleus than the third energy level. So the radius gets bigger as you go down, meaning that francium is the biggest, fattest element there is, and helium is the smallest. But if they ask you which has a larger radius, nitrogen or oxygen, and why, you would say that nitrogen has the larger radius because it has fewer protons in the nucleus, or it has a lower nuclear charge. Or you could argue that oxygen has the smaller radius because it's got more protons. That can also be your explanation, because they're saying the same thing in opposite ways. Ionic radius is the radius of the ion of an atom. In other words, when it gains or loses electrons for making ionic compounds. For nonmetals, the ionic radius is larger because you've added more electrons into the electron cloud, and electrons repel each other. So if you put more electrons, they're going to try to spread further apart. And for metals, it's smaller because you've gotten rid of some electrons. So if we consider the case of, for instance, let's go back to our good friend fluorine. We've got a nucleus in the middle, and then we've got 2 electrons in the first energy level, and we've got 1, 2, 3, 4, 5, 6, 7 in the second. So this is fluorine, which is 1s2, 2s2, 2p5. When it gains another electron, electrons repel each other, so they're going to kind of take that whole energy level, push it out a little bit more, make it a little larger. Right? On the other hand, if we were to consider our friend sodium, let's kind of piece this back together. So we're going to consider our friend sodium, which it's got one lonely electron out here in the third energy level. When sodium, which is a metal, loses its one electron to become Na plus, when it loses this electron there, it has lost that entire third energy level, and so it gets smaller. And in fact, if you were asked to compare Na plus to F minus, and you were asked to compare their sizes. Well, if we take a look at how this would look, they're both going to have the same electron configuration. They are isoelectronic with each other. Fluorine has this extra electron, or sodium has lost an electron. So they have the same electron configuration, but sodium has 11 protons in the nucleus. Fluorine only has 9. So that increased nuclear charge is going to pull those electrons closer to the nucleus. That's another little trend that goes with that. This right here shows you the atomic radii of the main group elements, groups 1 and 2, and 13 through 18. So you can kind of see the pattern that cesium is absolutely freaking huge, and helium up here is tiny. And we see that neon has a radius of 69 picometers, and sodium is 186. But if it loses that electron, it's now going to actually become smaller than neon. Or aluminum, if it loses its 3 electrons, it's going to lose its whole third energy level. It's going to become smaller than neon. Fluorine that gains an electron will become larger. Oxygen, when it gains 2 electrons, becomes larger. You can also see, if you look really closely, these trends are not perfect. There's a few ups and downs and bumps in the road, but it generally follows the pattern. You don't have to know the exceptions, like that neon is 5 picometers larger than fluorine. Don't spend all your time focusing on that. Now, for the trend that the College Board loves to ask about, you can be guaranteed you're going to be asked about ionization energy at least once, if not once on the multiple choice and once on the free response when it comes time for your AP exam. So, ionization energy is the energy required to remove an electron from an atom or an ion. So, you're going to reach in and you're going to pull an electron out. And what's called the first ionization energy is the energy required to remove the highest energy electron. There is a large jump when you start removing core instead of valence electrons. And the general trend for first ionization energies is that they increase from left to right across the periodic table because you're increasing the nuclear charge, the radius is smaller, so based off of Coulomb's law, it's going to require more energy to remove an electron. And ionization energy decreases as you go down a group. So as we go from, say, I don't know why this keeps shrinking on me. If we go from lithium to sodium to potassium to rubidium to cesium, the first ionization energy is going to decrease because that electron is further and further away from the nucleus. It's still experiencing a +1 effective nuclear charge in francium as in lithium, but the distance, so based off of Coulomb's law, since the distance increases or the radius increases, the ionization energy would decrease. And then this is saying, I'll talk more about this, that the ionization energy where an NP6 electron is removed is dramatically higher. So let's look at a few examples. So I'm going to take as an example, let's consider, magnesium. Magnesium's electron configuration is 1s2, 2s2, 2p6, 3s2. The first ionization energy would be how much energy is needed to remove the highest energy electron from magnesium. So you would be removing one of those 3s electrons. The second ionization energy is the energy needed to remove another one of those. The third ionization energy, you've now taken both of those electrons away, is going to be the energy needed to remove one of those electrons, and that's going to be significantly higher. So if we look at a Bohr model of this, which will help us visualize this a little bit, tell you, even though Bohr models are not a very accurate model of how electrons actually exist, they really help for visualization purposes. So the first ionization energy would be to remove, I don't know, say this electron right there. So that would require some amount of energy. To remove a second electron will require a little more energy. This may be not necessarily intuitive because the effective nuclear charge out here is the same. It's +2. But removing the first electron is a little easier because these two electrons repel each other. So that's kind of helping you to remove the first one. You don't have that extra repulsion when you go to remove the second one because the first one's already gone. Then, when you go to the third ionization energy and you try to take one of these electrons, there will be a massive jump in the ionization energies because you're removing what's called a core electron, one closer to the nucleus. So, if we look at this chart, this shows, for instance, the first ionization energies for the alkali metals. You can see it decreases as you go down the periodic table from lithium to sodium to potassium to rubidium to cesium. And then if we look at group 18, the noble gases, these are tremendously higher values. For instance, helium, it's 2,377 kilojoules per mole versus lithium's 520. So tremendously higher. Now, this shows you a chart of first ionization energies as we go through the periodic table. What's really interesting about this, there's a few unique features that you should be aware of. Let's see if I can. It's not going to let me draw on this. But the interesting things, so we start with hydrogen, and then we go to helium, where we've doubled the number of protons. Then lithium, that third electron goes way further out from the nucleus, so there's a big drop in the ionization energy. Then we go to beryllium, we've added another proton. Then we go to boron. There's a slight drop because the 2p sublevel is slightly higher in energy. In other words, those electrons already have more energy, so it's going to take less energy to take them away. It's like they're higher up in this, like you're reaching down into a hole to pull these electrons out. Well, the higher in energy they are, the closer to the top they are, the easier it is to remove them. So there's a drop here because you go to a 2p sublevel, which is higher in energy. Then we go to carbon, it increases. Then we go to nitrogen, it increases. There's a sudden dip with oxygen. And if you remember all the way back to the orbital diagrams with the 2p sublevel, what's happening with oxygen is the electron being removed in oxygen is paired because you have 3p orbitals, so the first 3 electrons go into separate p orbitals, and then with oxygen, that electron is paired, and that repulsion there makes it a little easier to remove an electron from oxygen. By the time you get to fluorine, you kind of overcome that by the fact that you keep adding protons to the nucleus. And then you get to neon. Then there's a huge drop when you go to sodium because that electron is much further away, much from the nucleus, much lower attractions. Then magnesium, aluminum, silicon, phosphorus. Here we have that dip right there because the electron being removed in sulfur is paired. And argon. Then we have potassium and calcium. And then we get into the transition metals where there's not a whole lot of variation. You're not going to be asked a lot about that. But then you go from arsenic to selenium. There's a much lower gap because of the pairing of the electrons, so forth. But you can see for all the noble gases, the electronegativities decrease as you go down the group. And for the alkali metals, lithium, sodium, potassium, rubidium, cesium, those first ionization energies decrease. So these are all first ionization energies to remove the highest energy electron. Here's an example free response question that you might see, and it's asking you how you would answer these questions as far as ionization energy is concerned. You have this chart with 4 elements. You have to read the question carefully because it does tell you that they are from the 3rd period of the periodic table, and the elements are numbered randomly. So use the information in the table to answer the following questions. So what you might notice first off is your first ionization energies. Since we're on the 3rd period of the periodic table, that starts with sodium and goes all the way to argon. So the ones with the lowest ionization energies are going to be furthest to the left, and the ones with the highest are going to be furthest to the right. Now, there's a few other things you might notice. For instance, with element number 2, its first ionization energy is 496. That's to remove one electron. To remove a second electron is 4,560 joules. That's a jump by a factor of 10. So this tells us that we had one electron that was easy to remove, and then the next electron was very difficult to remove. So this thing had one valence electron, which tells us that element 2 is sodium. For element 3, it takes 738 kilojoules for the first electron, 1450 for the second electron, and then 7,730. That's a huge jump for the third one. So this element, element 3, has two valence electrons. So the element in period 3 with two valence electrons is magnesium. And then we can tell that the elements 4 and element 1 are further across on the periodic table. We're not sure which one. We don't have enough data to make that conclusion. But what we can say is that element 1 could not be aluminum because it's got to be further to the right on the periodic table than element 4. So it could potentially be that 4 is aluminum and 1 is silicon. But we don't know that for sure. I mean, for all we know, this could be chlorine and argon. We don't have that much information. But when it's asking which element is most metallic in character, well, metals lose electrons. That's their defining trait. They have low first ionization energies. Element 1 has the lowest, element 2 has the lowest first ionization energy, so it's the most metallic. Then when it asks you to identify element 3, you would say that element 3 is magnesium because the large increase between the second and third ionization energies indicates that it has two valence electrons, and magnesium has two valence electrons. Or the high third ionization energy indicates removal of a core electron, so you have two valence electrons, it's magnesium. Then it asks you to write its complete electron configuration, which would be 1s2, 2s2, 2p6, 3s2. Then for D, what's the expected oxidation state for the most common ion of element 2? Well, since that's sodium, that's a +1. It easily loses an electron. Its chemical symbol is Na. And then it asks a neutral atom of which of the four elements has the smallest radius. Well, the one with the smallest radius is going to be the one with the greatest nuclear charge, since they're on the same period. So it's going to be the one with the most protons, which would have the highest first ionization energy. So that would be element 1. So that's just a sample of how some of these questions might appear. You'll have more questions like this, but in a multiple choice format in today's assignment that's in AP class. The next trend that we have is electronegativity, which is the ability of an atom in a molecule to attract shared electrons to itself. In other words, when it's in a covalent bond, they're kind of playing tug of war. The electrons aren't shared equally. Electronegativity is how strongly you're pulling those electrons towards yourself. Larger values of electronegativity mean stronger attractions. And they're kind of scored on a 0 to 4.0 scale, where which it's called the Pauling scale. Fluorine has the greatest electronegativity, it's a 4.0. Francium has the least. And generally speaking, the noble gases don't really have electronegativities because first you'd have to convince them to create a covalent bond. The reason that it increases as you get to fluorine is because the radius is smaller and the effective nuclear charge on the valence electrons has increased. So the electrons that are shared are valence electrons, the ones farthest away from the nucleus. Yeah, and for what should be obvious reasons, noble gases don't really have electronegativities. So here's a chart of electronegativities. You can see francium and cesium are down here really low. Fluorine's way up here, followed by oxygen and chlorine, and then nitrogen and bromine and sulfur. So these three up here are, well, really these four, or the most electronegative elements. Nitrogen, oxygen, and fluorine, because they're really small. So nitrogen and oxygen have Coulomb's law working in their favor because of the small radius. Chlorine has it working in its favor, and the other halogens because of the increased effective nuclear charge on the valence electrons. So that's electronegativities. And then this last one, it's really hard for them to ask questions about this because there's not a predictable pattern. This is electron affinity. It's the energy change associated when you add an electron to an atom. More negative values are associated with greater release of energy when you put an electron into an atom. The halogens have the most negative electron affinities. They release the most energy when you stick an electron in them. That should kind of make sense. But then nitrogen has no electron affinity. Same with the noble gases. But this is kind of this chart right here. You can kind of make what you will out of it. It's a little bit interesting to look at, but I don't really know that you're able to pick out really big patterns from this. Except that the halogens have pretty big electron affinities. They release a lot of energy when you add an electron to them. Chlorine more so than fluorine, even. The last couple things, just to make sure we cover this, is that valence electrons are the ones in the outermost shell. They're the ones in the outermost S and P sublevels. Elements in the same group have the same number of valence electrons, and so they behave similarly in chemical reactions. And last but not least, the periodic table is arranged in order of atomic number. You don't really need to know these people's names. You should have learned this before. But the periodic table is now in order of atomic number. If you look at, for instance, argon and potassium on your periodic table, you notice that argon has a higher average atomic mass, but it's got one less proton, so it comes first.